Hi people, this is the third of the three video segments that I'm preparing for the lecture that I missed on Thursday. We are moving to chapter 7, and this deals with beam elements. Now, if so far the structures that we have looked at were kind of bulky, and we meshed them, we divided them into finite elements with these things which look like a tetrahedron or a pyramid, four-sided pyramid. So these were called tet elements, and each at each node, if we are dealing with a four-noded element, linear element, each node had 3 degrees of freedom associated with it. In other words, unknowns. So display I-beam geometry, which we also modeled with these elements, but it was a bad idea to model an I-beam with tet elements. And I told you why, because I-beams usually are very long, and they have a rather thin web or a flange. And in order for us to get reasonable information with tet elements, we have to put sufficient number of tetrahedrons in the web or the flange area. That means that it's going to be small, very small elements there. And because the length of the I-beam is quite large, then we'll suddenly start dealing with potentially 100,000 elements to analyze an I-beam. There are other structures where using tet elements are not useful. For example, if you take the frame of a, let's say, a skyscraper or a high rise, okay, these are made of lots of beams welded together and bolted together, etc. Now these are relatively small elements or relatively small components in one direction, the direction of width and the height of the beam, and very long in the other direction. So these are more suitably used, more suitably analyzed with uh, beam elements. So what is a beam element? If you have a geometry which is one-dimensional in nature, such as a line, then what we can do is, it doesn't have to be a straight line, by the way. It can be a bent curve or a curve in general. What we're going to do is this geometry, we're going to divide it into elements, just like we did with the tetrahedral elements, except that these elements will lie on the line. So here is one element. Here is another element. Here is another element, etc. So this may be 4, 5, 6 elements. Okay? So here's a generic element that I'm going to put here, down here for you, so you can see what's going on. My generic element is basically a line segment. This is generic element I. It can have 2 nodes. This is linear element, linear beam element. Or it can have 3 nodes. Okay, this is element I. If you have 3 nodes, this is parabolic beam element. Each node has 3 translations as unknown. So let me write this UX, UY, UZ, and 3 rotations as unknown. So theta X, theta Y, and theta Z. You may recall that when you took your strength of materials book course or stress analysis course, you dealt with beam elements, and beam elements, not only displacement are important, but rotations are also important. So A node of a beam element has 6 degrees of freedom, 3 displacement and 3 translations. And beam elements are simply straight line segment, basically, that you can cover a line or a curve with it. I will now go and do an example, a very simple example, which is still not chapter 7. This is a prelude to chapter 7. It's just a straight line that we're going to model it with beam element. Now, by the way, remember in beam element, later on, you have to tell the software what is the cross section. The cross section, is it a circle? Is it a rectangle? Is it an I-beam? Because just saying that here's the line, here's the beam element, is not going to cut it. And what is the orientation of these things? For example, a circle really doesn't matter. Is the I-beam oriented like this, or is it oriented like that? So if you take this element, for example, its response is going to be different if the I-beam looks like that, or the I-beam looks like this. Okay, that's really the purpose of I-beam. Obviously, if the load is going down like that, you don't want it to be like so. You want it to be like that. Okay, so let's go and do a very simple problem in Catia. I'm going to minimize this. All right. We open a part file just like before. And I'm going to draw a straight line here. So one way to do that is just go ahead and sketch the line in one of these planes. So here's a line. All right, there. And as far as I'm concerned, this is my geometry. Let's apply, there is one other step that you have to go through here. When you create your geometry, which is later to be modeled with beam elements, you've got to join this geometry. So if we go to, and joining is done in wireframe and surface design. So you go to mechanical design, you're familiar with part design, assembly design, you scroll down until the third one from the bottom, you take wireframe and surface design, and the toolbar which says operations, this major toolbar in this workbench. So you click on it, join, and you go and select this curve. Nothing happens except that if you look in the tree, there is a join branch created here. All right, now we can apply. We can go back to analysis. We can go back to part design, or we can stay here. It really doesn't matter. So we're going to apply material to this thing. Let's go and make it out of, let's say, metal. Apply it to the part or the joint. It really doesn't matter. And we are done. Now we go to generative structure analysis. And notice that before, when we did that, we had solid object, we had parts, solid bulky parts. And obviously what Catia did, it immediately went and meshed that. Here, all I've got is a line. So Catia is not going to mesh a line for me. That's my responsibility, that's my job. So we say, okay. Now this model manager toolbar, so that I've told you that it's one of the important toolbars in Catia, we never, except for one occasion, we never had to go there. When Catia sees a solid object, automatically meshes it with this. But for us, we don't have a solid object, we have a line. And there is a beam element, okay? This is tetrahedron, and this is beam element. You click on the beam element, and then it says, okay, what is it that you want to mesh? Obviously, it's this line, it turns yellow. And what is the size of the element? Now, I don't exactly know what the length of this thing. I suspect it could be about maybe 5-10 inches. I'm not sure. But it's going to break it up into little elements like of this size. If you want, you can change this thing, or you can keep it the way it is. Or here you have linear elements or parabolic elements. I will leave it with linear. So we say OK. And then you can go and look at your mesh just like before. And there it is. Now, it's kind of hard to see what's going on here, but you can see that elements were created. When you select one of these things, there is the element number that's displayed. In this case, it's 20. excuse me, and then there are nodes that are created around it. All right, so this is it. Nothing fancy or exotic like we had for solid objects here. As far as this is concerned, we're done. Oh God, this allergy is killing me. Okay, the next thing we want to do first, we deactivate this plot. We deactivate this just like before. Now we can say what is the cross section of this thing. So if you look at the model manager, there's no way you can miss it. There's something that shows like a I-beam. It says 1D property. Later on, when we do shells, this says 2D property, and finally solid object 3D property. That we never have dealt with because this was done automatically for us. So we go to 1D property, you click on it, and then the support is this line, and there are different choices that you have. By the way, notice that as soon as I selected the edge or that line, the material that I put on the material on the part of that line was picked up. Now, there are different type of cross sections. There is the cylindrical beam, which is with circular cross section, a tubular, which means the pipe, rectangular, all kinds of things, including I-beam and box beam, etc. Now, we are going to assume this is a simple circular cross section. This is why it's right here. Now, how do we define the area or the radius of the cross section? You click on this wrench, and then you can put any radius you want. I'm going to put a 1 so that you can see it better. First of all, you can see right there. If you change this thing to let's say 0.5, the radius 0.5. For visual purposes, is displayed on the screen, and it looks like this. Good. Now, there's something else that's important here, which is orientation point. Now, remember, when you have an I-beam or you have a rectangular cross-section, etc., the orientation of this will affect the response of the beam. If it's circular, it doesn't matter. A circle, you spin basically this, or you twist, you rotate, revolve this about the axis, nothing is going to change. This is why when you have a cylindrical cross-section, cylindrical beam or a tubular beam, you can actually close this thing. You don't have to select orientation geometry. We're going to worry about this thing in class next week. So we say, okay. Now, this left end is clamped, for example, and I'm going to put a concentrated load at this. So basically, you have a cantilever beam. So I click on the load, distributed load, and selected this point, and I'm going to put it in the Z direction. So let's take this thing out. Let's put a minus 100 or 1,000 pounds. There it is. And you can see that right there. See? And this is it. So we're going to run this thing just like before. We're going to run it. Done. You can look at the deformation. You can animate it. Right there, you can see that. You can look at the displacements. So look at displacement here. Now, of course, displacement, these are shown in the form of arrow. We can change that can change our rendering. Unfortunately, my graphics card is not doing a good job here. This is not correct. I mean, look, I don't know, when I do this thing in class, this is not going to happen. But unfortunately, here, it does happen. Displacement are shown incorrectly. Now, unfortunately, you cannot plot them on mesostress. Okay? And let me put this thing back to text. Where is this? And you can see that the displacement of the nodes are shown by these vectors, and their x, y, z component, as you can see. Okay. So I'm going to stop this here. Please don't forget to save your stuff. You go to File, Save Management. File, Save Management. All of these things are open. So if we take the analysis, let's see now. This is the analysis file. These are temporary files. You don't have to worry about it. Save as. Desktop. New folder. Okay, so July 1. Everything is going to go there. Analysis and the part file. And this is the kind of thing that you're going to be submitting on the final exam. Your analysis file, your part file, and in the case that you're dealing with analysis assembly, later on we're going to learn that you have to submit the product file also. All right, guys, so please make sure you look at these 3 video clips. Uh, I'm not going to go through this basic stuff in class on Tuesday, and I will keep going with beam elements. Okay.